Now, in module 2 of chapter 4, we shall learn about a new type of derivative of tensors known as covariant differentiation of contravariant and covariant tensors and vectors, and also Ricci's theorem, a very well known theorem for tensor calculus, and repeated covariant differentiation. So, in this module we have three sections. First one is the covariant differentiation, second one Ricci's theorem, and the third one is repeated covariant differentiation. In module 2 we shall learn about covariant differentiation of contravariant and covariant tensors and vectors. Secondly, we shall learn about Ricci's theorem, and third, the repeated covariant differentiation. Now, from the transformation formula for a contravariant vector, we have this expression a k equals to del x k del x bar I a bar I. Now, differentiating partially both sides with respect to x j, we get del a k del x j equals to del x k del x bar I del a bar I del x bar n del x bar n del x j, the chain rule is applied here, plus del 2 x k by del x bar I del x bar j a bar I. Now, in the previous section we have obtained the expression of del 2 x k by del x bar I del x bar j. So, we replace that value in this expression. On solving, we get del a k del x j equals to minus gamma k u v del x u by del x bar I a bar I del v j plus del x k del x bar I del a bar I by del x bar n del x k del x bar I plus gamma bar s I n del x bar n by del x bar j del x k del x bar s a bar I. Now, replacing dummy indices I by s in the first term on right hand side, we find del a bar k by del x j plus gamma u j a u equals to, in the third bracket, del a bar s by del x bar n plus gamma bar s I n a bar t, third bracket close, del x k by del x bar s del x bar n by del x j. Now, if we write this expression, left hand side expression by a k comma j, then right hand side can be written as a bar s comma n del x k by del x bar s del x bar n by del x j. So, which is the law of transformation of mixed tensor of type 1 1. Again, from the transformation formula for a covariant vector, we find a bar I equals to del x k by del x bar I a k, and again in the similar manner, if we differentiate with respect to x bar j, we get this expression, which also contains a second order partial derivative at the right hand side in the second term del 2 x k by del x bar I del x bar j. Now, again replacing this term by the expression obtained in the previous section, we get this expression del a bar I by del x bar j minus gamma p I j del x k by del x bar p a k equals to del x k by del x bar I del a k del x l del x bar j, again chain rule is applied here, minus gamma k m n del x m by del x bar I del x n by del x bar j a k. Here also replacing the dummy indices k and l in the right hand side by t and s respectively, and k m n in the second term of right hand side by r t s respectively, we get this expression del a bar I by del x bar j minus gamma p I j a bar p equals to, in the third bracket, del a t by del x s minus gamma r t s a r, third bracket close, del x t del x bar I del x s del x bar j. Now, this shows that del a t by del x s minus gamma r t s a r follows the transformation law of tensor quantity of type 02. This tensor is defined as the covariant derivative of covariant vector with component a t and denoted by a t comma s. Thus, a t comma s equal to del a t by del x s minus gamma r t s a r. So, this is known as the covariant derivative of a covariant vector with respect to x s. Similarly, covariant differentiation of contravariant vector a k will be a k comma j, and its expression will be a k comma j equals to del a k by del x j plus gamma k t j a t. So, now covariant differentiation of tensors of type 02 can be defined in the following way: a I j comma h, that means a I j is a covariant tensor of type 02, and we are doing the covariant differentiation with respect to x h, and you are getting this one, that is equal to del a I j by del x h minus gamma t I h a t j minus gamma t j h a I t. Similarly, for the mixed tensor of type 1 that is a I k and its covariant derivative with respect to x j is denoted by a I k comma j, and its expression will be del a k del x j minus gamma l j k a I l plus gamma I j l a l k, which is a tensor of type 1-2. So, when we perform covariant differentiation, the rank of covariant tensors increases by 1. So, if a tensor of type p q is covariantly differentiated, then it will be a tensor of type p q plus 1. Similarly, we have a I j comma h, that means a I j is a contravariant tensor of type 20, and its covariant differentiation with respect to x h will give us the expression a I j comma h equals to del a I j by del x h plus gamma I t h a t j plus gamma j m h a I m. In general, the covariant derivative of a tensor of type PQ is given by the following expression: A I1 I2 IP J1 J2 JQ comma K equals to del A I1 I2 IP J1 J2 JQ by del xk plus these expressions, which is the general formula for the covariant derivative of a tensor of type PQ. This is the expression, and for covariant index the negative sign is coming, and for contravariant index positive plus signs are coming. Now, let us see an example where Aij is a skew symmetric tensor and its covariant differentiation has been done with respect to xj. Then the expression will come like this: 1 by root g del del xj root over g Aij. Now, we know that Aij comma k by the previous expression, we know that Aij comma k equals to del Aij by del xk plus gamma I kr Arj plus gamma j rk Air. Now, putting k equal to j and summing over it, we get Aij comma j equals to del Aij by del xj plus gamma I jr Arj plus gamma j Rj Air. Now, from the property of Christabel symbol, we know that gamma j Rj have the expression like this: del del xr log root g. So, putting the value, we get this expression. Now, replacing r by j, we get the following expression: Aij comma j equals to del Aij by del xj plus gamma I jr Arj plus del del xj log root g Aij. Which can be again expressed in the following way. That means, in the third term, log root g can be expressed as a half log g. Now, again replacing j by p and r by j as their dummy indices, we get Aij comma j equals to 1 by root g del Aij del xj plus 1 by root g del g del xj Aij plus gamma I jp Ajp. And which one can be expressed in this way: 1 by root g del del xj of root g Aij plus gamma I pj Ajp. Now, as Aij is a skew symmetric tensor, then we can express this way: gamma I pj Ajp equals to gamma I pj A pj by replacing p to j, and by using the skew symmetric property, we get minus gamma I pj Ajp. So, gamma I pj Ajp equals to 0. Thus, the above expression is coming to Aij comma j equals to 1 by root g del del xj root g Aij. So, the second term is vanished due to the above expression. Now, you see another example, that if APQ is a skew symmetric tensor and a pq comma r equals to a pr comma q, then a pq comma r is equal to 0. Let us see the solution. A pq comma r equals to a pr comma q, it is given. Since a pq is a skew symmetric tensor, so a pq comma r equals to minus a rp comma q, that is equal to minus a rq comma p by using the property given, and that is equal to a qr comma p using the skew symmetric property, that is equal to a qp comma r, and that is again equals to minus a pq comma r. So, twice a pq comma r equals to 0, that means a pq comma r equals to 0. Now, grad phi is denoted by phi comma j when phi is invariant. That means phi comma j is nothing but the partial derivative of phi with respect to xj, and that can be also written as del phi del xj. Also, a I comma j minus a j comma I, and if we just express a I comma j minus a j comma I, then we shall get del a I del x j minus del a j del x I, which is nothing but the curl of the covariant vector a I, and it is a tensor of type 0,2, and it is denoted by the curl a I. Now, this example is also an important example, that is a I comma I. A I is a contravariant vector, rather components of contravariant vector, and we are taking the covariant differentiation of a I with respect to I, and which gives the expression like this: 1 by root g del del x I a I root g, where g is the determinant of g I j, obviously not equal to 0. Now, by the definition of covariant derivative of contravariant vector, we have a j comma I equals to del a j comma del x I plus gamma j k I a k. Now, contracting j and I and summing over I, we get a I equals to del a I del x I plus I k I a k. Which gives the expression del a I del x I plus del del x I log root g a I by using the property of Christabel's symbol. Now, this a I sorry now থেকে বলছি. Now, this a I comma I is called the divergence of the vector a I and is denoted by div a I. Now, a vector is irrotational if curl a I is equal to 0. That means a I comma j is equal to a j comma I, that is del a I del x j equals to del a j del x I. In the previous section, we have learned about a new type of derivative known as covariant derivative of contravariant and covariant vectors and tensors. In this section, we shall learn about the covariant differentiation of fundamental tensors and Kronecker delta, and we shall see that they behave as constant with respect to covariant differentiation. After Ricci's theorem, we shall see some properties of this type of derivatives. Now, we state Ricci's theorem, which is given by the following way: the fundamental metric tensors and the Kronecker delta behave in covariant differentiation as constants. Now, for proving this one, we just see that g I k comma j is equal to 0, g upper I k comma j equals to 0, and del I k comma j equals to 0. Now, by the definition, j I k comma j equals to del g I k del x j minus gamma L j I g L k minus gamma L j k g L I. Which can be written as del g I k del x j minus Christabel symbol of first kind j I comma k minus Christabel symbol of first kind j k comma I. Now, using the property of Christabel symbol, we get this one del g I k del x j minus Christabel symbol I j comma k minus Christabel symbol k j comma I, and this is equal to 0 because the expression for the second and third term is coming to del g I k by del x j. So, we get g I k comma j is equal to 0. Again, for g I k upper I k, g upper I k comma j equals to del g upper I k del x j plus gamma I j L g L k plus gamma k L j g I L, and again by using the properties of Christabel symbol, this coming to 0. And also for del I k comma j equals to del I k by del x j minus gamma L j k del I L plus gamma I j L del L k is equal to 0. Hence, Ricci's theorem is proved. Now, let us see some applications of the covariant differentiation, that a I k b j s comma L equals to a I k comma L b j plus a I k b j s comma L. That means, it follows the product rule with respect to covariant differentiation, and this can be easily proved by taking a I k b j s as c I j k s, and using the covariant differentiation we can prove the result. We can also prove this one, g I j a I comma k equals to a j comma k. Now, again by the product rule we can write g I j a I comma k equals to g I j comma k a I plus g I j a I comma k. Since g I j comma k equals to 0, so we get g I j a I comma k equals to g I j. Now, in the right hand side, a I comma k can be expressed in the following way: del a I del x k plus a t gamma I t k. So, from the expression denoted by 2, that is Gij ai comma k equals to Gij del ai del xk plus at gamma I tk, we can easily prove that it takes the form aj comma k. Now, in this section we shall see the repeated covariant differentiation of invariant and contravariant and covariant vectors and tensors. Now, if phi is an invariant, then phi comma j is a covariant vector, because it is a partial derivative with respect to xj. Now, if we denote phi comma j as aj, then aj comma I is a second order covariant derivative of phi. So, we can write in this form phi comma ji equals to aj comma I. Hence, phi comma ji minus phi comma ij equals to aj comma I minus ai comma j equals to del aj del xi minus del ai del xj. As aj is del phi del xj and ai is del phi del xi, so replacing the values we get del 2 phi del xi del xj minus del 2 phi del xj del xi, and this expression is equal to 0. For higher order covariant derivative of tensors, it is not in general commutative. Now, ai comma j comma k, that means ai is a covariant vector, its covariant derivative is done with respect to xj, that is written as ai comma j, and again covariant derivative is done with respect to xk, that means ai has covariant derivative of 2 times, one with respect to xj and another one with respect to xk, which is denoted by ai comma jk, which can be expressed as in the following way, and which takes the form this one del 2 ai del xk del xj minus del am del xk gamma m ij minus am del del xk of gamma m ij minus del ap del xj gamma p ik plus as gamma s pj gamma p ik minus del ai del xp gamma p jk plus as gamma s ip gamma p jk. So, this is the expression for the covariant derivative of second order for a covariant vector. Now, we can easily prove that ai comma jk minus ai comma kj. So, if I perform ai comma kj and the expression of ai comma jk is given above. So, if we subtract, we can get the expression am r m I j k, where the expression for a r m I j k will be equal to del del x j gamma m I k minus del del x k gamma m I j plus gamma p I k gamma m p j minus gamma p I j gamma m p k. This tensor is a tensor of type 1-3 and it is called Riemann-Christabel tensor of second kind or the curvature tensor of the Romanian space. So, from the second order covariant differentiation of a covariant vector, we are getting the expression for curvature tensor of the Romanian space. And it is clear that R m I j k is a tensor of type 1-3 and its associated tensor R h I j k can be obtained by inner product of GHM with RMIJK, and this associated tensor RHIJK is known as Riemann-Christabel tensor of first kind. And clearly AI comma jk is not equal to AI comma kj, and if they are equal, then RMIJK equals to 0. That means curvature tensor is identically 0. In that case, it is called a flat space. Riemannian space whose curvature tensor is identically 0 is called a flat space. Now, let us see some properties of Riemannian-Christabel tensor. RMMJK, that means the contraction has been done for the upper index and the lower index, first lower index. RMMJK equals to 0, RMIJK equals to minus RMIKJ. That means curvature tensor is skew symmetric with respect to the last two covariant index. Also, RMIJK plus RMJKI plus RMKIJ equals to 0. This is called Bianchi's first identity, and also RMIJK comma L plus RMIKL comma J plus RMILJ comma K is also equal to 0. This is called Bianchi's second identity. So, the last two equations are known as Bianchi's identities. Now, for Euclidean space with its line element in rectangular Cartesian coordinate system, where dx square is given by dx1 square plus dx2 square plus dot 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 dxn square, all gij's are 1 for I equal to j, and for I not equal to j all gij's are 0, and in that case all Christabel symbols vanish. So, the Riemann curvature tensor also vanish. Now, the scalar curvature is defined by the contraction with Gij Rij, and that is equal to denoted by R. Now, a space for which the Ricci tensor, this Rij is known as Ricci tensor, is equal to lambda Gij, lambda being invariant at all points, is called an Einstein space. A space where the Ricci tensor is a multiple of Gij's is known as Einstein space. Now, let us see that for an Einstein space of dimension n greater than equal to 2, Rij can be expressed as a R by n Gij. The value of lambda is nothing but R by n. Now, from the definition of Einstein space, Rij equals to lambda Gij. So, operating by Gij from both sides, we get Gij Rij equals to lambda Gij upper Gij. Now, the left hand side expression will give R, the scalar curvature, and the right hand side expression will give lambda n. So, lambda is equal to R by n. Now, let us see that R m j comma m equals to half R comma j. Now, Bianchi's second identity gives us this relation RMIJK comma L plus RMIKL comma j plus RMILJ comma k equals to 0. Now, contracting m and k, we get this expression. Now, for the first term, when m and k is contracted, it gives r I j comma l. Similarly, for the second term it gives r I l comma j, and for the third term it is coming r m I l j comma m equals to 0. Now, again taking product with g I l, we get this expression, and this gives the expression r l j comma l minus r comma j plus r m j comma m equals to 0. Now, changing the dummy index L to m, we get r m j m equals to half r comma j. Now, this is another expression. If a I j equals to r I j minus half del I j r, then we can see that a I j comma I equals to 0. From the above expression, we can find that a I j comma I will be equal to r I j comma I minus half del I j r comma I. So, a I j comma I, and from the previous example we get that it is coming to half r comma j minus half r comma j equals to 0. Now, for an Einstein space, the scalar curvature is constant. Now, for an Einstein space, we have seen that r I j equals to r by n g I j. Now, taking the inner product with g I m, we obtain this expression, and from here we get r m j equals to r by n del m j. So, now taking covariant derivative, r m j comma m equals to r comma m by n del m j, and which gives half r comma j, that is r comma j equals to 0. The scalar curvature is constant. So, in module 2 of chapter 4, we have learned about Ricci's theorem, that is the expression for fundamental metric tensor under covariant derivative, and the repeated covariant differentiation of invariants, contravariant and covariant vectors and tensors, and various properties of curvature tensors and Einstein space, and some related examples. Thus, we end this chapter 4 with this module, that is module number 2.